Greetings. Welcome back to Unit 3 of AP Physics and Mechanics over Work and Energy. And in this chapter, we're going to be covering the magic of conservative forces and how those relate to potential energy and potential energy graphs. So to start, I officially want to go over the two types of forces that you're generally going to have doing work on an object. And these are either going to be a conservative force, which are a little bit rarer, or most forces, which are going to be non-conservative. So a conservative force is something that does zero net work in a closed path. And a closed path kind of looks like this diagram down here, where like you could be going up in one way, but then as long as you go back down and you reach the same place that you started from originally, you're technically in a closed path. You haven't really gone anywhere new at the end of the day from beginning to end. And so the magic about these forces and them doing near zero net work is that generally the work that they do is independent of the path that the object takes. So if, say, an object here is under the influence of gravity and it takes this path all the way up here through here, another object under the same influence of gravity taking a path from here through here would have the same net work done on it as the other path. And we noted this a little bit a while ago on one of the work examples we did, where there was a block falling through a circular track. In that example, it was notable that, like, you know, all we really needed to do to get the work done by gravity, which is a conservative force on that track, was to calculate the force due to gravity and multiply that by the vertical displacement that the object had. And in all scenarios, as long as the object is displacing through that vertical distance, gravity is always going to do the same amount of work. Now, there are really only two conservative forces that we're going to be looking at for right now, and that's gravitational force, as I just noted, and spring force, which we're going to elaborate on in a second. If it's not a conservative force, then it is a non-conservative force, and these are forces that generally can cause a loss of mechanical energy. Now, the work done here, because you could be under the influence of something like, say, friction over a longer distance, means that the work done by these forces generally do depend on the path an object takes. If you have more distance to travel and friction is, affecting you, then obviously taking the longer path is going to be less efficient overall because friction has more time to drain energy out of your system. So generally, if it is not gravity or spring force in mechanics, it is a non-conservative force. So gravity and springs are the only two that will obey this zero net work and path independence principle. Now, why conservative forces are so important is because these are the forces that directly give us something called potential energy. So if you have a conservative force like gravity or a spring force that's doing work, either one of two things is going to happen. If positive work is done by this force, then obviously the object gains kinetic energy because positive work gives you a positive change in kinetic energy. But if negative work is done, then the object is going to lose kinetic energy. And obviously that energy has to go somewhere, and it's not necessarily going into friction because we're not losing any mechanical energy per se. So instead, we say that that lost kinetic energy is stored in the form of potential energy. And so we have this back and forth relationship going on, or an exchange or a trade-off, whereas the kinetic energy of an object decreases from a conservative force doing negative work, the potential energy of that object that's stored into its system is going to increase as a result. So if we want to express mathematically this change in this object's potential energy, it can be expressed as the negative of the change in kinetic energy. So change in kinetic energy is equal to negative change in potential energy, or you could flip-flop them. So instead you could say change in potential energy is the negative of whatever the change in kinetic energy is. Again, all this is referring to is that if one is increasing, the other has to be decreasing. You could also express it in the integral form of the work formula, where if we think about how work or a change in kinetic energy is equal to the integral of force with respect to displacement through some bounds, well then if we take that and we just find the negative version of it, then we could express the change in potential energy as the negative integral of force with respect to displacement. And that's what we're going to be using for this next derivation. So gravitational potential energy is based on the gravitational force. And we're going to refer to that as Fg equals negative mg. We're going negative there because we'll kind of assume generally that we're going to be lifting an object upwards in the positive direction, and gravity is pointing downwards. So when you're lifting an object up, that's when the force due to gravity is doing negative work. So that's when we're storing potential energy. So if we've got that force acting on an object, the change in gravitational potential energy can be given by this derivation here. So the change in gravitational potential energy would be the negative integral from some initial height to some final height of the gravitational force, so negative mg, with respect to dy. And so there's no real dependence on a displacement coordinate here, so we can just kind of take the integral of effectively a constant. So we would just add in x, and if we do the fundamental theorem of calculus with that, we would get this formula here, which is mg hf minus hi, or mg times the change in height that the object experienced. So in general, gravitational potential energy is equal to mass times acceleration due to gravity times whatever height the object gains from being lifted. Now note, I put a little red asterisk there next to the h, because this equation does have a bit of nuance to it. We'll say that this is relative to a position where the gravitational potential energy is 0. And it's an interesting thing with potential energies. You actually have a lot of freedom in what you choose to be the 0 point. Because you can technically have a negative potential, we'll get to that a lot more in universal gravitation, you get to choose where the floor, so to speak, of your problem is, or the floor that you're lifting stuff up from. Energy is very flexible in that regard. So in this case, this formula usually works as long as you're careful about where your 0 point is, generally just the lowest height that you reach in your problem. Now, the next conservative force that I want to focus on relates to springs. And when you have a spring and you're applying a force to it, the relationship between the force that you apply and the resulting distance that it stretches or compresses from its natural resting length, which we'll call equilibrium, is given by this fun little equation right here. And this equation is known as Hooke's law. It was coined by Robert Hooke, who was famously Isaac Newton's arch nemesis. There are a lot of funny stories about the beef between those two. Now, with spring force, it's worth noting here that the force that you're applying is directly or linearly proportional to how much it's being stretched or compressed. So if you say stretch a spring by a displacement x with a force F, if you were to apply a force 2F to it, it would stretch by a distance 2x. So it's a pretty direct, nice linear relationship. Very easy to do labs with this formula. And the quantity K in your equation right here is the spring constant, given in units of newtons per meter. And this characterizes the spring's stiffness qualitatively. So like if you pick up a spring and you try to stretch it and you really struggle, that's because it has a really high spring constant. It takes a lot of newtons to stretch that spring over a distance of 1 meter. So that's kind of how you can interpret the units of that. And so with Hooke's law, we can also derive our formula for elastic potential energy. And so very similarly to the gravitational force one, if we have a spring force given by negative kx acting on an object, the change in elastic potential energy, same using that formula over there, is going to be the negative integral of our force, negative kx, with respect to dx. And we'll just assume our bounds are some initial position over to some final position. And if we integrate that, it actually does have dependence on the position vector. And so when we integrate that, we'll have to do the reverse power rule. So we'll end up with 1/2 kx squared, essentially, for our antiderivative. And if we plug in our bounds from there, we will end up with 1/2 kxf squared minus xi squared. And so in other words, if we're starting from equilibrium and we just stretch it some distance from equilibrium, then the formula for elastic potential energy is 1/2 kx squared, where the red asterisk there is just saying this is contingent on x being the distance that the spring is stretched from equilibrium. So just from where it normally chills under no forces acting on it. All right. In this example, we've got a particularly long spring that varies with the displacement according to the function f equals negative 0.01 x squared. Note, because of the x squared there, we can say that this spring does not obey Hooke's law. So we're going to have to integrate this manually. We can't just use the equation for elastic potential energy here. Our first goal is to determine how much work must be done in compressing the spring from x equals 0 to 35 meters. Now, this statement, how much work must be done to compress the spring, really is just a roundabout way of asking how much potential energy is stored in the spring. The reason we can interpret it as such is because the force function that we're given here is the restoring force, and the person who's actually applying the work to the spring to store the energy in it is applying the opposite of this force. They're pulling against the spring's restoring force. And so really what we're looking for here, or finding the work of, is a positive version of this force. But in a roundabout way, we could also just imagine we're trying to find the change in potential energy of this spring. In that vein, we're going to start with the change in potential energy formula, which is delta U, and it's elastic potential here. And that's going to equal the negative integral of the force we're given with respect to dx. Now, plugging some stuff in here, we're going to keep that negative sign out front, but we are going to add the bounds to our integral. So we're integrating from 0 to 35 meters. And then the function we're plugging in here is negative 0.01 times x squared dx. Now at this point, I'm going to evaluate the antiderivative, which means I'm going to get rid of the integral sign and replace it with some brackets, just to indicate that we are changing this into our antiderivative function. So within the brackets, well, first, actually, I will pull out the 0.01 and get rid of the negatives because we have a double negative. So we will end up with 0.01 out front. And then within our antiderivative brackets, if we perform the antiderivative of x squared, we will end up with 1/3 x cubed. Close our brackets, and the bounds that we're going to be plugging into this for the fundamental theorem of calculus are 0 to 35. Now this is going to equal, well, 0.01 divided by 3 would turn into 0.0033. A little ugly. And then within our bounds for fundamental theorem of calculus, it's going to be 35 cubed minus 0 cubed. So 35 cubed minus 0 cubed, close brackets. And at this point, we can go ahead and evaluate. And if we do, we should find that the elastic potential energy stored in this spring is about 141.5 joules. Very cool. All right, so part 2 has us determine how much work is done in decompressing the spring from 35 to 25 meters. And then we're going to determine the velocity that a block of mass 2 kilograms would get if pushed by the spring through that distance. And for this problem, it doesn't really mention it, but we'll go ahead and assume that the block maybe starts from rest, so we don't have to worry about any funny business there. So in this case, first thing I'm going to do is go ahead and make use of the fact that we've already really integrated this thing before, because we're going to have to do the same operation again, just with different bounds. So this little green asterisk over here just means I'm creating a portal in which I'm summoning that step halfway through the work of the previous part. So change in potential energy for this spring, we can express as 0.01 times, within brackets, 1/3 position x cubed. And then the bounds that we're going to be evaluating here are initial position, 35 meters, and final position, 25 meters. Notice again, the bottom is always the initial, the top is always the final. And in this case, it's going to evaluate a little weirdly because we're going from a larger distance to a smaller displacement. So with that in mind, we'll go ahead and evaluate again. So out front, we're going to have 0.0033 for 0.01 divided by 3. And then within our brackets, we're going to plug in our bounds. So it'll be 25 cubed minus 35 cubed, close brackets. And if we evaluate that, we'll find that our change in potential energy here is about negative 90 joules at the end of the day. Now that's a change in potential energy, but we're looking for a change in kinetic energy if we're expecting to find some kind of velocity. And so for that, we're going to use the relationship between change in potential versus change in kinetic, that the change in kinetic energy of an object is going to be the reverse or the inverse or the negative of the change in potential energy that that object experiences. So in this case, our change in potential was negative 90, so our change in kinetic energy is going to be the negative that, which is positive 90 joules. Okay? And with that, we can now define maybe change in kinetic energy. Ooh, that's a gross K. As 1/2 mass times, I'm gonna again lump velocity squareds together and just subtract them from each other directly. So it would be 1/2 m times Vf squared minus Vi squared. And if we plug in our numbers there, we're gonna say 90 joules is equal to 1/2. The mass of our block here is 2 kilograms. Nice and convenient. That'll cancel out with the 1/2. And then times the Vf that we're trying to find squared minus, well, again, we'll go ahead and make that 0 squared. We'll assume it's starting from rest. And so here, the 0 we don't have to worry about. The 1/2 and the 2 will annihilate into a 1. And so really we're taking the square root of 90 to get our final velocity. So the square root of 90 will give us our final velocity of about 9.5 meters per second. Cool. All right. So the big trick here, again, really is being careful with your bounds, making sure that positive and negative signs are being consistent, because that can totally throw off your math. And you may have to suspiciously hand wave away some negative signs if you're not careful. Beyond that, just making sure that you're always keeping in mind the relationship between kinetic energies and potential energies here is important. Now, another thing that we can do with potential energies, now that we have those formulas, is go in the reverse direction. So we know that potential energy is the antiderivative or the integral of force with respect to displacement. And because we're using the term antiderivative here, then technically we could still also state the converse of that, which is that force then must be the derivative of potential energy with respect to displacement. So we can express that simply as force equals the negative derivative of potential energy with respect to x, or the change in potential energy over change in position. Now, generally, when you're doing this, you're finding the magnitude of a conservative force. And the forces that you find this way are always going to be pointing in the direction of decreasing potential energy. You're finding the slope of the force that's kind of driving the object towards a lower energy position. And related to this, because now we have forces that we can get from potential energies, is the concept of equilibrium positions. So, I mean, when we were studying forces, we would say that an object was in equilibrium when the net force acting on it was 0. And so then in terms of potential energy, because force is the derivative of potential with respect to x, this would be when the derivative of a potential energy function with respect to x is equal to 0. Same thing. So then if you have a graph of potential energy, kind of like this thing over here, there are generally 3 types of equilibrium that you could experience. So the first is stable equilibrium. And this is shown as a local minimum in the potential energy function. That would be something like this spot over here, point C, where the graph kind of reaches a little dip or a trough in the function. So an object that's in stable equilibrium is going to stay there and not go away if you were to perturb it or push it in one direction or another. So in other words, say you were to stick a marble somewhere in a track in this little half pipe here. If you were to poke that marble, it's just going to kind of oscillate back and forth. It won't really like go off into the distance. It'll stay where it is and eventually return back to its equilibrium position if there's some friction acting on it. That's as opposed to unstable equilibrium, which would be these 2 points over here, B and E. These points on this function are known as local maximums on the potential energy function. And again, if we go by the marble analogy, say you were to place a marble at this peak at point B here. Well, sure, if you try really carefully, you could maybe balance it at that peak. But if you were to even so much as breathe on the marble at that spot, it would fall off from that unstable equilibrium point and it would just keep going. It would not, it'll go away and never return to that point. And instead, it would either just keep going until it goes off into the void on either side of this graph, or if it has too little energy, it will just kind of sink into the nearest stable equilibrium position, like C over here. And finally, a little less important, but still worth noting, is neutral equilibrium. This would be like points A or D, where the graph is just kind of flat. Again, it has 0 slope there, like the other 2 points, but an object in this position I guess you could think of it as like there's just no force acting on it for the foreseeable future. So if you were to perturb it, Newton's first law would take into place. It would just keep going at constant speed, but it wouldn't really do anything all that interesting. You don't really see stable or neutral equilibrium points too often, but again, it is worth noting. So finally, before we jump into some examples of some of this stuff, with potential energy graphs, they can be a little hard to wrap your head around. It's kind of like motion graphs and how to interpret those a lot of the time. It's a big struggle area for a lot of physics students. So potential energy graphs track an object's potential energy at different positions of x continuously through some kind of interval. And I already mentioned it with kind of the marble example in the previous section, but I think a helpful intuitive approach to these graphs is to just kind of think of them as roller coasters or tracks that you can roll around a marble on. So I took this GIF here from the lovely website, My Physics Lab. And what I have here on the right is what's physically going on. We have a marble that's kind of moving on a track, so to speak, between 2 points. And notice there's no friction here, so it's just allowed to keep going. Now, interestingly, it looks like over here on the left, we're just kind of mirroring that animation. But what this is quite literally the potential energy versus displacement graph. And notice it is pretty much a one-to-one copy of the physical scenario over here. So a lot of the time, a potential energy graph quite literally is the exact physical scenario you're trying to model, like a roller coaster. And for that reason, the marble analogy is pretty good for what it's worth. So there are a couple of concepts to remember with these graphs as you're analyzing them, and it can help save you some time if you're trying to figure out what to do for what the question is asking. The first is generally just to note again that as the potential energy is decreasing, so as say the marble gets to a lower position, its kinetic energy has to increase because that energy has to go somewhere. It has to be exchanged. The next thing is that an object in stable equilibrium generally is going to oscillate back and forth forever, as long as there are no non-conservative forces acting on the object, like you see over here. And again, if you were to place maybe the marble over here in this little trough, again, it would oscillate back and forth. But note that it would not have enough energy to go above where it starts. The next thing, and sometimes you will see this, is that the total energy that the marble, so to speak, would have at any point along this graph is comprised of some potential and some kinetic, some combination of those two. And that total energy, as we're going to find with conservation soon enough, cannot change. Whatever energy it has, it cannot gain or lose as long as there are no non-conservative forces. And finally, we talked about it on the previous couple of sections, but the slope or the change in potential over the change in distance is the force acting on the object. So notice like wherever the steeper slope is, quite literally slope, again, if we're going with the marble analogy, the higher the force pulling that marble down to a lower position. And the shallower the slope, the less force is accelerating or decelerating this marble in the moment. So again, I highly recommend you kind of take this intuitive approach to these graphs because I think it helps you interpret them a lot more nicely. But if you can keep these concepts in mind, analyzing these graphs won't be so bad. And with that, let's go ahead and employ some of these concepts in a couple of examples before we finish out. Into the potential energy graph examples. So here we've got a particle with a mass of 1 kilogram, nice, and it's released from rest at point A, right over here, and it begins to slide towards position B, right over here. So in part A, the problem is asking us to estimate the force that's acting on the object at position A. So we're trying to extract a force out of this potential energy graph. Now for that, recall that the force from a potential energy curve is always going to be the slope of this graph, or in other words, the rate of change of potential energy. So we would say it's the negative du over dx. Now we don't have a function to work with here, so we can't really take a derivative of a function. So instead, we're going to treat this like the just kind of estimated rate of change of the thing, or delta u over delta x. And we can express that as the negative change in potential over change in x. So it would be u final minus u initial divided by x final minus x initial. Now we need to estimate the slope of the graph at point A. And so for this, it could be a little challenging maybe if the graph was super crazy and curved all the way through, But our kind of light at the end of the tunnel here is that the graph does look fairly linear all the way down to maybe about here somewhere. So if we can get some definite points along the line there, we can kind of approximate it as a linear slope. And if that's the case, then our estimation should be pretty decent for the slope. So obviously point A, we have a definite coordinate for us. So we'll go ahead and use that as one of our points, maybe the initial. And then the next one that looks pretty decent looks to be about right here at 1 meter, because we can intercept a little dotted line with the graph right there. And at that point, it's looking like the energy at about 1 meter is 5 joules. So we'll treat that as our final point, xf, and this will be our initial position, xi. With that in mind, we'll go ahead and plug our stuff in. So we'll say that our estimated force is approximately equal to the negative. Our final potential is 5 joules minus our initial energy, which is 10 joules. And we're dividing that by the difference, which is going to be simply 1 minus 0 for our initial position. That means that our force is going to be roughly equivalent to negative 5. So we've got a double negative there, and that's going to give us an estimated force of positive 5 newtons acting on this object. All right. Now in part B, the problem is now asking us what the object's change in potential energy is as it travels from point A to point B. Now, when you're being asked about this and you have a potential energy graph, you don't really care about X in the moment. All you're really looking at is the difference in the Y values. So here, we're just looking at the potential energy we're starting at, and we're finding the difference between that and the potential energy we have down here. Now, from that, it appears that our potential energy at point A is approximately 10 joules, and our potential energy at point B, where we're ending up, is about 2 joules, if I'm lining things up right. So with that then, our change in potential energy would be just our final minus initial. So it would be 2 joules minus 10 joules, which would give us a change in potential of negative 8 joules. Now again, kind of like in the last example we did where we had to consider the relationship between change in potential and change in kinetic, if we want to find the equivalent change in kinetic energy, which is the next thing that it's asking for in this part, well, the change in kinetic energy relates to change in potential by being the negative rate of change of the other. So if one is decreasing, the other is increasing. So because it looks like potential energy is decreasing in that interval, kinetic energy must increase, and therefore it will change by positive 8 joules in response. So that is our answer for kinetic energy. And that leads directly into part C, where we're being asked to figure out the object's speed as it passes through point B. So if you remember that animation on the slides of the dot kind of, bouncing around between the two sides of that fun looking curve, this is kind of how you would estimate roughly what speed it has at different points around that graph. Now we're looking for a change in kinetic energy between points A and B, so I'm just going to label it as such. And we'll say that that is equal to 1/2 times the mass of the object times the final velocity squared minus the initial velocity squared. Now here we have all of our values we need to plug in, so we'll go ahead and do that. We have positive 8 joules equaling 1/2 times the mass of the object, which is 1 kilogram here, times the final velocity, which we're trying to solve for. And, oh, yes, okay. And in the original text of the problem, it says that it's released from rest at point A. So our initial velocity here is going to be 0 meters per second squared. Now, at this point, we just need to multiply both sides by 2 to get the 1/2 over on the other side and VF by itself. And so if we do that, we will find that VF squared equals about 16. And so if we were to square root both sides, we would find that our final velocity for this problem between points A and B would be about 4 meters per second. That is our answer. Cool beans. All right. So let's see what we got next. Ooh boy. All right, this is a spicy one. We've got a particle of mass 2 kilograms, and it has a potential energy function that is given to us here. So spoiler alert, we're probably gonna have to do some calculus here. Now, X is in meters and U is in joules, pretty standard. And we're being told that only conservative forces act on the particle, so we're not gonna have any funny business with friction here. This graph sketches out that function, roughly, We're shown a couple of different potential energies here that line up with specific positions, just so we have those as a reference. So part A here is asking us to determine the numerical values of x1 and x2 along this graph. So right here and right here, and identify each of those points as either stable or unstable equilibrium. Now, the last part of that kind of gives away exactly the trick for how we're going to find those two coordinates. And so right off the bat, I'm going to go ahead and identify these as certain types of equilibrium. Now, remember that if it's a dip or a relative minimum in a potential energy function, that is always going to be classified as stable equilibrium. Because like, imagine you were to place a marble in this path here, it wouldn't really be able to escape. It would just kind of oscillate back and forth between those 2 points. That's as opposed to this hill looking equilibrium point over here, which is unstable. And that's because, like, sure, even though you could maybe balance the marble at the very, very, very tippy top of the hill, if you're careful, if you even so much as nudge it or breathe on that on either side, it's going to slip down and approach a lower energy state, whether that be a stable equilibrium point or just the void down on this right side. So with that out of the way, the next thing is determining the numerical values. And where do we start with that? Well, the first thing we should note is that we have a definition for what exactly establishes equilibrium. We know that equilibrium happens when force is equal to 0. And we also know that force is equal to the derivative of a potential energy function with respect to x. So in other words, we're really looking for where the derivative of this function du over dx is equal to 0. With that in mind, over here to the right, I'm going to go ahead and take the derivative of this function, just so we have it on hand for anything we might need it for later. So here, I'm going to be a little quick with the derivative. I'll assume you're pretty comfortable with it, but feel free to work it out in more detail if you're not sure. But here we've got, effectively, this term right here would be 3x minus 3. So the derivative of 3x minus 3 would turn out to just be 3 as a constant. We would just knock out that x term. And then we're subtracting from that x minus 3 cubed, which we can use the chain rule for. So we would treat the outside first. We would take this 3 down. So it would be 3 times, and then this whole term squared. So it would be x minus 3 squared to complete the derivative. All right, and that is du over dx. So now over here, we're just going to write that out again. We're going to say 3 minus 3 times x minus 3 squared must equal 0 if we're looking for x1 and x3. Now here, we can move maybe 3 times x minus 3 squared over to the other side, just so we get rid of any negatives. And we'll end up with 3 times x minus 3 squared equals 3, effectively. Now at this point, we could divide both sides by 3, and in doing that, we'll end up with x minus 3 squared equals 1. And if we square root both sides, we will end up with x minus 3 equals plus or minus 1. That means that our solutions for x here are going to be 3 plus or minus 1 meters. Now, that means that we basically take 3, we'll add 1 to it, we take 3 and we'll subtract 1 from it, and those will become our 2 points. So over here, x1 will be the smaller value because it's closer to the origin. So it'll be 3 minus 1, which is 2 meters. And then x3 over here is the one further along, so it'll be 3 plus 1, and that will be 4 meters. So those are our 2 equilibrium positions. All right, next part B. We're being told that the total energy, so the sum of kinetic and potential of the particle, is 40 joules. And knowing that, we're being asked to figure out the particle speed at x1, so at the 2 meter position. So for this, the total energy, if we'll go ahead and establish as k plus u, if that's equal to 40 joules, well, it seems like we're going to need to evaluate what the potential energy is, or figure out what that is, so that we're allowed to solve for the kinetic energy, which is our unknown here. So with that, the good news is we know what x position x1 is now. And because we have our potential energy function, we can plug that position into our function to get how much potential energy we have at that point. So over here, u at a position of 2 meters would be 3 times, well, we plug in 2 here, it would be 2 minus 1, minus, then plug in 2 again, it would be 2 minus 3 cubed. And evaluating all of that, we'll end up with a potential energy at this position of about 4 joules. And now with that, we can go ahead and solve for our kinetic energy, because K will equal 40 joules minus the potential energy at a position of 2 meters. So that will be 40 minus 4, which is about 36 joules total. So because we have 36 joules of kinetic energy, all we need to do is equate that to the formula for kinetic energy, which is 1/2 mass times velocity squared. So our mass is 2 kilograms, and the velocity is what we're solving for, so it's okay to leave that there. Now all of that is going to equal 36 joules. Now thankfully the 1/2 and the 2 will annihilate with each other and just become 1. So V squared equals 36 joules, or well, technically not joules anymore, so maybe we'll get rid of that. But V squared equals 36, so if we want to solve for the velocity, we take the square root of both sides, and the square root of 36 is thankfully a pretty simple solution. It is about 6 meters per second. So that is our particle's velocity at that position. Neat. All right, part C has us just do a sketch. And for this, we're being asked to sketch a graph of the force on the particle as a function of x. Now, thankfully, we've already derived our formula for force here, mostly. There's a bit of an asterisk there. So note that we're going to be using our equation that we derived up here for this part down here. So that's where I'm getting that information. Now, I said we mostly have it because if you go back to the slides, remember that the force on a particle as, well, in relation to the potential energy is technically the negative derivative of potential with respect to distance. So it's negative du over dx. That means that we need to take the negative of this function so that it properly represents the force as a function of x. So here, we're just going to kind of flip the signs on everything. So it'll be 3 times x minus 3 squared minus 3. That is our function of x. So to me, this looks like a quadratic graph that's going to dip a little bit below the x-axis because its y-intercept would be -3. Well, it's not its y-intercept, but you get the idea. It's shifted down by 3. So then, because it looks roughly quadratic, I'm just going to sketch a roughly quadratic shape. And we just want to note that, again, f is equal to 0 at the points x1 and x3, because we did that in part A over here. So noting that our x-intercepts are at those 2 points, I'm just going to draw a roughly quadratic shape that goes whoop, and that is a really terrible parabola. I am notoriously bad at drawing those, but that mostly gives a good picture of what this graph is doing. Just note that it's going to kind of gradually get steeper and steeper as time goes on. I think I've actually just made it worse. Now, before I dig myself into any more of a hole there, I'm going to move on to part D. And in part D, we're being told that if the particle is released from rest at 1/2 x1, so that's right here, half of x1 would be just 1 meter, it looks like, based on what we know x1 is. We're being asked to find its speed as it passes through x1. So here, we need to figure out, I guess first, the potential energy at 1/2 x1. So we need to find the potential energy at a position of 1. So we'll go ahead and plug that into our function. So it'd be 3 times 1 minus 1, our given function up here, minus 1 minus 3 cubed. And if we evaluate that, we should find our potential energy at this point right here, if I mark it. So E3, if we're looking at our little grid lines here, is 8 joules of stored potential energy. And we've already solved for U2. We did that back over here, and we know that that's 4 joules. So I'll just kind of rewrite that down here to remind us of that. It is 4 joules by the time it falls down to x1. Now with that, if we can find how much the potential energy changes, then again, we can use this relationship from the slides that kinetic energy is the negative of potential to get us ever closer to the final answer. So first, we need to find the change in potential energy. And so for that, it's going to be final minus initial. So it'll be U2, which is also a nice rock band, minus U1. So in this case, it'll nicely just be 4 joules minus 8 joules, which is a change in potential energy of -4 joules. Now, we can use the relationship that change in kinetic energy is simply the negative of the change of potential energy. And if we say that, then our change in kinetic energy will correspond to this by being +4 joules. So we lost 4 joules of potential energy and we gained an equivalent amount in kinetic. Now at this point, we just need to solve for the velocity. So again, kind of like we did back up here, the kinetic energy can be expressed as 1/2 mv squared. So our mass m is 2 kilograms, and we're solving for final velocity. I guess here we'll note it's vf squared minus v initial squared, and because it's starting from rest, we can claim that that is 0 for our initial velocity, and all of that is equal to +4 joules. So doing the victory lap here, again, our 1/2 and our 2 will annihilate out with each other. 0 doesn't really matter. So all we're really doing here is taking the square root of 4 joules. So if we do that, it's the square root of 4, which is nicely 2 meters per second. So as a particle, if it starts from rest at this point right here, it falls down to this point right here, it will have attained a speed of 2 meters per second. Now, quick conceptual note, if we were to start the particle at that height, it would fly all the way down here, it would reach a 2 meter per second kinetic energy, and then it would start increasing its potential energy again, and its kinetic energy would correspondingly go down. And because this is at the exact same height, so to speak, as this point over here where the unstable equilibrium is, presumably a marble that we would place on the track right here would kind of oscillate back and forth between these two positions. It doesn't quite have enough energy to get over this hump, but instead it will either oscillate, or if maybe we're lucky, it'll come to rest at this unstable equilibrium point, assuming it doesn't get too perturbed. So potential energy graphs can be a little confusing, but I hope this video helped clarify a few things, or at least showed a couple of the tricks that you can do with these graphs if you're being asked to work with them. That is about it for this video. It probably turned out to be a long one, just based on how long I've been filming. I'm glad you bared with me for a little bit longer, and I hope the video helped. So next up, we've been jumping through some hoops here, but we're going to be moving on finally to the principle of conservation of energy, which makes a lot of the hoops we've been jumping through here a little redundant. So until then, I will catch you in the next one.